All right, so you are responsible for hydrostatic bearings, even though I haven't covered an example problem. There's a good example in the book, and I would mark page 573. Look over it, look at the figure there as well as the equations, because I could ask you questions about that on the coming exam. All right, so that would finish off plane bearings. The next topic we need to talk about is springs. As a matter of fact, I usually like to cut up the class at springs. In other words, at springs I like to say, okay, that's enough information. We'll stop here and have another test. Since I have already put keys, couplings, and seals on an exam inadvertently, I think what I'll do is go through springs and electric motors, and then we'll have our test. Okay, that'll be our next test. So we'll cover all the way through electric motors, and then that'll only leave us brakes, clutches, and gears, and linear motion elements. And we'll focus on that for the final. Yes?
So this next test will be bearings, springs, and electric motors?
Yeah, see, the way I break it up is just according to the list I've got here.
Yeah.
That's the idea, right? All you got to do is just look at the topics, and that was supposed to be the first exam. Instead, I accidentally included this one. So belts and chains will have to be included here, and I won't do that. Normally, this is supposed to be the second exam, but without this, so I'll add in electric motors. So that's why I have them organized this way, to make it easy to see where we're at. So let's turn on this module so you can see it. It's visible now. And we'll open up the presentation on springs, but not that way. I use a lot of animations in my slides. Well, sometimes I do, sometimes I don't. And animations don't show up in brackets. Well, I guess it will download it eventually. While we're waiting for PowerPoint, can you think of any place where you've seen a spring used?
Everywhere.
Everywhere, right? Okay. Springs are very common. Sometimes they're easy to deal with, sometimes they're a pain in the butt, like when you're trying to replace brakes on the rear end of a rear-wheel drive vehicle that has drum brakes. I swear I bloody up my knuckles and swear like a sailor every time I have to do that. But they're used there. And then, you know, why are the springs, excuse me, a few of you know my pain, right? A few of you have done this, okay? Why are those springs so stinking difficult? Well, why do they have to be so stiff?
Trying to stop a very heavy vehicle.
Stop a heavy vehicle, right? You need to generate a significant amount of force. So how do you decide what the stiffness should be? As a matter of fact, how do you design the stiffness? What do you think, before we get into the lecture material, what do you think it would take? What parameter would you change to control the stiffness of a spring? Now understand we're talking about just regular linear springs. What is the number one parameter, do you think, that allows you to control the stiffness of the spring? Yeah.
Is it the distance between coils?
Distance between coils? Do you mean the number of coils, total number of coils, or do you mean how much they're spaced apart?
Usually it's how much the shape is, and if it's spaced together, it's a lot more stiff, and if they're stressed apart, it's easier to compress.
Okay. Anyone want to agree or disagree?
It's an extension or a compression spring.
So there are extension and there are compression springs. We're thinking of wound springs at this point, okay?
Diameter of the wire. Yeah.
Diameter of the wire.
The gauge of the spring.
Okay, so that's the gauge. What do you mean by the gauge of the spring?
The thickness of the wire that makes up the
Thickness of
coil.
the wire, okay. All right, any other thoughts? Okay, well, certainly the material, somebody said material, the material that the spring's made from, the diameter of the wire, those make a difference. The number of coils do make a difference in the stiffness of the spring, right? If you think about having two springs that are end-to-end that are extension springs, you have a softer spring. In other words, the amount of force required for a given deflection is less. In other words, the higher the number of coils, the lower the stiffness of the spring. Okay. Well, we'll get to all that in just a minute. Was there anything else? I thought someone else had anything. Excuse me. There are many different types of springs. So far we've been talking about helical coil springs. There are also, though, torsion springs that are also coils, but they're used in a different manner, and the type of stress in the material is different. As a matter of fact, one of the reasons you have to have strength of materials before you take this class is because of springs. Springs are a very important place where we use our knowledge from strength of materials. But there are also flat springs. Anybody ever see a flat spring on anything? On what? What do you got? On a vehicle? Almost, those are leaf springs, I think.
Well, I mean, some of them, you have a single, like, cover spring, especially on trailers.
On a trailer,
It's not a
perhaps?
full
Okay.
leaf spring.
Okay.
There's some like, brake, excuse me, brake pads, and then they're not like actually made to be springs, but it's called a wear sensor. It's actually like designed just like a flat spring. Whenever you press down on the brakes, whenever your sacrificial like element is like gone, it'll like push into your brake rotor
Mhm.
and make like a screeching
Make a
noise.
noise,
That
yeah.
you let off, it'll let the tension off of it so it stops making noise.
Yeah, you're right. I hadn't thought of that as a flat spring, but you're right, it is. Yeah.
Going back to the vehicles, we have a Model T that the rear springs are flat springs on now.
Really? I would love to see some, you know what? I bet there's some pictures of that on Google already. What is it?
It's a Model T Ford. It's an old dump truck version.
Okay.
So,
And is it the rear springs, front
Yeah.
springs, or?
they're like that, so that way when you put a load down in the back of the bed, they actually ride on the bumpers, which makes it a lot rougher ride, but make sure you don't lower your springs down on them.
I don't see them. I was hoping we could find a picture of just the rear springs. Oh, like this? Is this it?
Yeah, kinda like that.
Okay, now this looks like it's a leaf spring because it goes all the way across.
Well, that's like a regular truck one, which we
Okay.
also have, but like, my grandfather, he has a Model T dump truck, which is apparently the last remaining example of one.
Oh, really? Okay.
And
Neat. Is there a way you could possibly get some pictures for us?
I do not know.
Well, if you can, that'd be great. If you can't, it's okay, I understand.
Well,
But yeah, if you have the
look up-
chance.
Look up Helper Springs.
Yeah, now a helper spring is also technically a leaf spring though.
Yeah.
I thought of getting helper springs for my truck. I always go and, I think what you're thinking of is this type. So that there's an extra spring that
Yeah.
goes on.
It's almost
They are
like
shackled at
this
each end, and so they're technically a leaf spring at that point, instead of a cantilevered spring. That's the key difference between a flat spring and a leaf spring, is that the flat spring is like a beam that is cantilevered, whereas over here, think of it as a simply supported bridge that is supported either end. So this the type of stress and the amount of stress is very different in these two. Where all was I going? Oh, I was gonna tell you about the springs that I've thought about putting on my truck. Every time I go and get a load of wood in my pickup truck, I've got sides on the back, so it's, you know, when I try to go down the road, it's a little six-cylinder, it's a full-size truck with a six-cylinder, so going down the road with that box and pushing through the wind, you can tell that the box is on the truck, okay? It's not very easy, and of course I have to put on my hazard lights and go a little slower. One of the other problems is that whenever the truck is fully loaded, especially if it's hardwood, so it's a little denser and full, the truck will tend to sit and almost bottom out the springs. And so I've thought of adding helper springs. The problem with adding a permanent helper spring, oops, that's not what I wanted to do. The problem with adding a permanent helper spring like this is that then the spring is too stiff when there's no load on the vehicle. However, they've got this type, which are a bladder type. You add them in, you can add pressure or remove air pressure, and that way you can vary the stiffness of the spring, if you will, with and without load, which is really convenient. But if I added these to my truck, I'm afraid I'd have twice as much money in the truck as I've got right now. So I haven't done it yet. It's not that far, so I just let it bottom out and go home slow.
I'm gonna put an air shock on it.
Well, that's almost what this is, all right? It's just an air bladder. Yeah, I guess I could put air shocks on. Are air shocks cheaper? Are they? I might have to. So you can change the pressure on them, I guess?
Well, on my old truck, I put air shocks on it, but then I remote mounted an actual like air compressor with a valve and a switch.
Well, that's basically what this is, isn't it?
Yeah.
These are air shocks, yeah.
But it was really, really cheap. I mean, it was
Was it?
less than $100 for everything.
I looked into these, and maybe I was looking in the wrong place, because I seem to remember it costing several $100s for the kit. And I thought, I don't know if I want to put that money into this old truck. There are many other types of springs besides that. There's Belleville Springs. These are Belleville washers. And these are really interesting because you can tune the spring constant by either putting these back to back, so you make a stiffer spring, or face to back. Okay, so if they're kind of like that, I can't do it well, it looks like I'm trying to do shadows or something, but if you put these, imagine taking this, turn it around 180 degrees and put it together, then you actually make a lower spring constant spring. So you can tune the spring constant by how many washers you have. The more you add, the lower the spring constant if you're putting them back to face and so on. So that's interesting. The difference though, these are typically nonlinear. Most of these other springs, especially these, are more linear springs. Now this is also a nonlinear spring. It's called a constant force spring. Has anyone ever seen a constant force spring? They're pretty common in things like watches, or, well, actually I'm not sure watch. Maybe more just a helical spring. I don't know if I can find the picture of the one I've got. Let's see. They're not going to have it. My dad loves caves. So I've been, being a kid, I've been to just about every cave in this area you can imagine. And along the way, one of the things he's always afraid of is running out of light, right? You don't want to get into a cave where it's dark and not have light. So he's always liked flashlights you could wind, because he felt that, you know, as long as he can wind up a flashlight, he can find his way out. Of course, you know, I guess if you run out of energy and you lay there and die after a couple of weeks, you're not going to find your way out anyway. You can't charge the flashlight. But anyway, so he bought a flashlight, and of course, he ends up buying them and then giving me things once he has lost interest in it and sees that it actually is not that great. He gave me this big old flashlight. It's about this big, and half of the appeal of this light is the fact that it's got a clear plastic housing on it, so you can see what's going on the inside of it. It's got this handle that you turn out and you crank, and you wind up a spring. Well, what are you doing? Well, you're winding up a constant force spring. The way these things work is typically you've got another take-up reel over here, and as you wind it, you've got a ratchet and ball that keeps it from going backwards, at least until you turn the flashlight on and release it and allow it to go backwards. But the amount of torque required as you deflect this spring does not change. In other words, if you were to just grab a hold of the end of this spring and pull, the force versus deflection would be constant. You deflect it more and more and more and more, and yet the force remains constant. You're still putting energy into it because the force times distance is work, right? Anybody ever seen this used in an industrial environment? Right.
We've got one that's set up as a counterbalance on our ceiling.
Okay.
So it's basically applying constant force to the top of the ram to support it so that the motors don't have to lift it.
So it's kind of like a garage door, but with a constant force spring instead of one that varies.
Yeah.
Okay, all right. Someone else? You pointed up here? I've never taken one of these apart. I've wanted to, but they're so expensive. I've never.
They've got a constant rate, no spring there wound up.
Is it that type, or is it the type that's more like a spiral spring? I don't know. I've never taken one apart.
It's flat
It
stack
is?
like the
Okay.
constant rate
Well, it could
springs.
be then.
Almost like the recoil for a lawnmower.
Well, the recoil for lawnmower is different. With the lawnmower, as you pull it and deflect it farther and farther, the amount of force actually increases. It's got a low spring constant, that's why it doesn't feel like a lot of difference, but it's still, the more you deflect it, the stiffer, the more torque it's actually putting out. Yeah. We won't talk about that. That type is interesting because it's not a simple torsion spring. It's actually spiral wound, so it's flat. So all the coils are in one plane, essentially. So that's an interesting spring, but it's not exactly a flat spring. Now it is thin, and so it acts more like a flat spring. The place I've seen these used in industry are for door closers. So if you have a sliding door, for example, and you want a spring to pull it back, you may have had a screen door in the home you grew up in, you open the door and it slams shut. Why? Because there's an extremely high force at the beginning, right, that pulls the door very hard. These constant force springs can be set up so they'll pull the door with a constant force, and still it will accelerate, but not as bad as a linear spring does. So that's one place I've seen that used in industry. So energy storage and the constant force is a nice feature of that type. There are many other types of springs as well. Here's a flat spring, and you can tune the characteristics of a flat spring by changing its cross-section. So if you look at this from the top down, you've got just a simple cross-section. You can easily make this spring highly nonlinear by changing the cross-section and tune it to whatever you want. We won't talk about how you design that. Go ahead.
So Nike came out with a shoe recently, and they actually
Yeah?
has like a carbon fiber plate in
Okay.
the base of it that has kind of like acts like a spring. It's called Nike 4%.
Nike 4%?
Yeah. And then, yeah, carbon fiber plate.
We gotta see this. Which one do we want?
Second row, second one over.
This
And
one?
Yeah.
Okay.
So it kind of breaks it down, where you can see the foam on top, the plate in the middle, and the foam on bottom.
Okay, so this plate in the middle is the spring then?
Yeah, well, that's kind of like the argument. It's like, is it a spring, is it not a fixed spring? So like, as the foot kind of like propels off, it's supposed to provide a little extra give
Yeah.
and everything, so,
Interesting.
yeah.
Yeah, the concept of springs in clothing and in shoes and everything is actually interesting because there's all kinds of places where you might use it. If you're interested, I'll tell you a story about a friend engineer of mine who made a very interesting article of clothing. You wouldn't think of this, but as engineers, there's all kinds of things you have to work on that you might not otherwise think about. I will tell you one example. When I was in chemical engineering, we were seniors, we had people come in from, I think it was Procter & Gamble, I can't remember who it was, somebody that makes diapers. And the engineers were quickly talking about the mass in the baby's diaper and how much liquid is in the diaper and talking about all these. Of course, we know exactly what they're talking about and we're all feeling a little disgusted, but this is everyday conversation for them, right? Because think about it, it does make sense. If they make diapers that leak, the baby's going to get a rash, right? This is something you have to think about. And those concepts of mass and controlling liquid motion and all those things are very important. So anyway, I'll tell you one-on-one about a product my friend worked on if you're interested. I'm not going to mention it on camera. But it was a very interesting product, and he found some very interesting mechanical engineering phenomenon to be concerned about. So, and it involves springs. But anyway, he ended up helping a lot of people with the product he made, so I was glad he did it. Unfortunately, his product hasn't really taken over the market like I'd like to see it do. But anyway, so we're talking about springs and the fact that leaf springs, flat springs, can be made to be nonlinear if you wish pretty easily. Now, a leaf spring is very different from a flat spring. It's like a flat spring, but basically it's like one cantilevered to the wall, right? Because there's no rotation here in the center that's allowed because you've got a mirror image on the other side. And so a leaf spring, because of the way it's supported, is a lot like a flat spring, but you kind of get two springs for the price of one out of it. Again, we won't talk about this type, but you can tune the deflection, the force versus deflection characteristics by the length of the various plates here and their cross-sectional shape. So these are nice because you can basically, and if you have some spacing between these, which they typically do, what you can do is you can actually make the amount of force increase as the deflection increases even farther than a regular linear spring would. So here's the Belleville Springs that I told you about, where you can put them face to back or face to face, back to back. And this arrangement increases the effective spring constant as this does, but then being face to face here decreases the effective spring constant of these two together. Again, one of the problems with this is that they are nonlinear. But this would be a lower spring rate. This one would have a higher spring rate, and all that's been done is the two middle washers have been turned the opposite direction. You can add as many as you want and change the characteristics of the spring. Yes, sir?
What exactly do you mean when you say they're nonlinear?
What I mean, most of the time when we talk about a spring, what equation do you think of as soon as I say a spring? What do you think of? F equals kx. That's a linear relation, right? The farther the deflection x, the force is proportional to it, right? So bigger deflection, bigger force, just proportional. This is not that way. As you compress these springs, the amount of force required for the next eighth of an inch of deflection will be different than what was required for the last. You see, it's not proportional. The force is not proportional to the displacement. It does increase, right? I mean, the farther you squish any of these, the more force you're going to have to apply. But
Did the spring constant go up or down?
that I'm not sure about. If I remember right, the spring, I haven't designed with these, and I remember learning about them. If I remember right, the effective spring constant goes up, meaning once you squish this farther and farther, it takes more and more force. Okay? I remember it does. Okay, let's find out.
Would it kind of be in a curve? Because
I've
once-
seen them used before, but I've never understood.
Once you get past when the points would like get.
Is it more like progressive or degressive? As far
That's
as
what
it
I'm
goes?
saying.
I mean, I know the total force goes up.
Right, and that's what I'm saying, is it goes up faster, if I remember right. But let's find out. Load versus deflection. Okay, so their standard, load versus deflection. We can zoom in. Looks like their high load is more linear. Standard, actually, it looks like I'm wrong. The slope would be the spring constant, right? And so if the slope goes down, that means you get more deflection for less force. So it's degressive instead of progressive. Yeah, you're right. Force limiting, I didn't even know they had this. I'm glad we looked this up. We'll include this as a link in the slides. So eventually it looks like it gets to a certain point and the force no longer increases. Force adjusting, that's interesting. Let's see. Interesting. I don't know how that one works, but that's interesting. So certainly non-linear, but the nice thing is you can even put them together and tune them, get what you want out of it. So you said you've seen them used, where? On what?
I've seen them used in different racing applications for
Okay.
bump stops or travel limiting. They go on shocks.
So that would be a decent size spring then, that's not just a small
I've seen that, and I've also seen them in limited slip differentials.
Okay.
for upper ground cross.
Thank you for sharing. I learned something. I love it when I learn something. It's more fun. So as we said, a constant force spring has the same amount of force regardless of the deflection. Here's some examples from Professor Dew's experience again, where you see two different types of springs. This spring is just the typical wound spring. This also technically is a spring. Now these are usually called vibration isolation dampers, but if you think about it, it's just a block of rubber, right? And so all that happens is it deflects given the load that's on it. So what's the difference between a rubber spring like this that can deflect and this spring? What are some differences that you can think of? Any ideas? Linearity is one of them. Okay? Rubber springs are not linear. There's another big difference though.
Amount of deflection.
What's that?
The amount of deflection.
So the spring constant range can be different, but these are fairly thick springs.
I mean, this kind of connects to thermo, but I would say with like the coil spring,
Mhm.
there would be like less like energy lost to thermal energy, whereas like in the rubber block,
Right.
all of that energy would be absorbed and then given off as heat, whereas in the metal spring, it would just be transferred from one to the other. with
That is a
minimal
huge difference. That was the one I was going for, is that this type of spring is a lossy spring, whereas this one doesn't lose as much energy. Now, these actually do lose energy. Okay, if you look at springs, they do have a hysteresis curve. In other words, the amount of force you apply to compress is different than the force you get out when you uncompress. You have to put more force in per distance versus what you get out. It's not a huge difference, but it is there. As a matter of fact, there was a, I guess we'll get to that in a minute when we talk about materials. I'll save it for then. So here's some more springs. You can see that these don't have as much what's called coil clearance between them as the previous springs. These have a lot of coil clearance. Now I'm not sure if the reason for that is that these are lightly loaded at this time and these are heavily loaded, or if they're designed that way. But one of the design features is not just the diameter of the wire, but how much clearance you expect between the two, or you intend to put between the two. How would you decide how much coil clearance you need? Any ideas?
Would it be related to the amount of total deflection the spring will experience at whatever worst case maximum load it might endure?
Absolutely, yes.
Also seems to me that like the more coils you have, the more of a damping action the spring would have.
Now you said damper. I'm glad you said that. Why do you think there'd be more damping action?
I mean, there's more, not necessarily more distance, but there's more there's more of a load on the spring, at least I think there would be whenever there's more coils like that and a higher diameter, but like on the previous picture where there were less springs, or less, I lost my train of thought.
I understand, it's okay, it's okay. You're
I don't
trying
know
to
how
make
put it
it.
in words.
Okay, that's fine, go ahead.
If there was too much clearance between each coil, wouldn't it have a tendency to bow?
That's a good question. What about buckling? What about when the spring comes out of plane? Now, I'm sure you've all taken apart a ballpoint pen that you can click, right, and found the spring, and you start to compress it, and all of a sudden it flies outside of this, right? There's a name for that. That's called spring buckling. Okay? And one of the design parameters we'll care about a lot is at what force and deflection will the spring buckle, or will it at all? That's something we care quite a lot about. So you might realize the end treatment makes a difference, because the end is what helps support the spring and prevent it from buckling out of the axial line. All right, good discussion. I like this. I'm glad we're recording it. Maybe I'll make my presentation better off of this recording. So here's speaking of the flatness, notice this feature here, these two welded pieces of pipe or tubing or whatever that happens to be. Why on earth do you think that's there?
Locate the spring.
Locate the spring, keep it from moving out of position, make sure that the ends are oriented properly. And here's a place where no mechanical springs are being used. There are just isolation dampers. So these are supposed to lose energy on purpose. They're supposed to convert some of the vibrational motion into thermal energy.
They can also use those to electrically isolate.
Electrical isolation is another big reason. Yep, you're right. On the other hand, if you have a static problem, then you have to ground the machine. So here's an example of some flat springs being used. You can't see it, but this end is not rigidly connected up here. And so while it's bolted on this end, it can pivot on the other end. So these are flat springs. All right, so what we're used to seeing is F equals Kx. This is the linear spring equation. It says that the farther the spring deflects, the force increases proportional to that deflection. Okay. Now, if you have parallel springs, then to get the effective spring constant, you just add all the springs constants together. I remember being a kid, and I think I told you, Dad, you guys, my dad was a bodybuilder when I was a kid. So I remember going to the Y, and me and my sisters would sit there. We were probably 5, 6, 7 years old. We'd sit there while Dad did his workout, bored the whole time, you know, getting into trouble while he had to stop his workout to calm us down and then go back. And I remember he also had some things at home, and I don't know what to call them today, but I guess if you worked out with these things without a shirt, you'd call them chest hair grabbers. You ever seen those? They got two handles on either end. They got a couple of extension springs you can add or subtract. And you're supposed to do this with it, right? And of course, if you get it too close because it's hard, you could grab your chest hair, which is very painful. I know as a kid I tried that, and I finally figured out how to do it. I'd put my foot on one end and pull up with the other end, right? That's how I pulled the spring when I was a kid. So why did I tell you about that? Well, the more springs you add to those things, the higher, the harder it is, the more force versus deflection is required. And all you do is you just add the spring constant of each of those individual springs. Let me show you what they look like. There's got to be a good picture online for this. Let's see. Shocking or basically images. Yeah, they're still selling them. They're basically like this. I guess they took inspiration from me. That's what I used to do, except it was just the type that had the two handles. But the more springs you add in parallel, the more force is required for the same deflection. Okay? Now, if you take springs and you put them in series, imagine taking those springs. Say me and my sisters got a hold of one of those and we took it all apart, and say there were 4 or 5 springs. We put them all end to end and we start pulling on them. How much force versus deflection do you think would be required? It would be a whole lot less, right? You're making a softer spring. You've probably seen these equations. For serial springs, or springs in series, to get the effective spring constant, you take 1 over the sum of the inverses of all the spring constants together. Now there's a place where parallel springs are used, and I really like this example. Let's see if we can follow it, follow the link. I may have shown you this in dynamics. Let's see if you can remember this. think I've also got it, here maybe, yeah, there it is. Remember that? So see all these springs over there? Are those springs in series or parallel? They're parallel, right? Now, they're long springs, but you can see that they're connected together, each to the ends of two plates, right? So